This presentation examines how machine learning can resolve the contested authorship of Civil War love letters attributed to General George Pickett. These letters, published by LaSalle Corbell Pickett after her husband's death, have long been suspected by historians to be her creation rather than genuine correspondence, but quantitative verification methods have been lacking until now. This research extends beyond history to applications in document authentication, forensics, and detecting AI-generated content. The letters hold significance as potential contributors to the lost cause narrative, a post-Civil War reframing of Confederate motivations. LILA dataset includes LaSalle's known works, approximately 280,000 words, demographically similar imposters, approximately 1.2 million words, and the disputed letters, balanced by genre, 94% historical and biographical and 6% fiction, to prevent classification bias. Pre-processing removes OCR artifacts and creates 4 text versions, undistorted plus 3 distorted views using Stamatatos' method with k-values of 20,000, 3,000, and 300 frequent words. This systematically preserves stylistic markers while removing topic signals. The Siamese SBERT architecture processes text pairs through neural networks with shared weights to create comparable embeddings, following the winning PAN 2023 approach with corrections to documentation contradictions. Modified contrastive loss with margin parameters of 0.75 and 0.25 pulls same author text closer when needed while pushing different author text apart, creating an optimal embedding space. The primary challenge is cross-genre verification. Models tend to learn superficial genre markers rather than deeper stylometric signals, requiring techniques forcing focus on style over content. Text distortion addresses this by masking infrequent words, preserving stylistic signals while removing topic indicators. This is the first neural application of this technique for authorship verification. The second challenge involves scientific reproducibility, resolving contradictions in the original architecture documentation. Evaluation uses 5 complementary metrics: AUC, C at 1, F1, F0.5U, and Breer score complement, capturing different performance aspects across operating thresholds. Implementation uses AWS's Elastic Compute Cloud GPU infrastructure, PyTorch, and Hugging Face for modeling, and the scientific Python ecosystem for analysis, maintaining reproducibility throughout. Rigorous testing with 36 unit tests containing 168 explicit assertions, expanding to thousands of runtime checks against generated test data, ensured 93% code coverage and verified all components. K-fold cross-validation and parallel training across distortion views ensures inferences rely on stylistic markers rather than content signals. Optimizations, including strategic sampling and parallelization, reduced runtime from 1.8 years to 6 hours. Hyperparameters were determined through 89 controlled experiments and literature review. The model achieved 0.996 overall score versus 0.607 baseline, maintaining a score of 0.962 even on heavily distorted text. External validation on VALLA achieved 0.801 overall, would rank 5th in PAN 2020, demonstrating generalizability in contemporary verification problems despite increased difficulty. Applied to the Pickett letters, 74% were classified as LaSalle's authorship in the undistorted case, mean similarity of 0.709, with consistent attribution across all distortion levels. For this analysis, each letter chunk was paired with 10 random LaSalle chunks, creating 820 to 2,160 inference pairs varying by distortion level, all held out from training. This evidence aligns with historians' suspicions based on anachronistic content like Little Round Top not used by soldiers during the actual battle. Novel contributions include the first neural application of text distortion for authorship verification, an open-source historical verification framework, state-of-the-art architecture reproduction and clarification, and evidence for the authorship of the Pickett letters. Future work could incorporate longer training, named entity recognition, explainable AI techniques, and tighter expert collaboration. All code and data are available on GitHub, with modular design for application to other historical verification questions. Thank you.